This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. Welcome to our third lecture. What you can see on the screen is a list of today's presenters of assignment 4. So we'll do that after the break in about approximately 1 hour. And this will be the order of the presenters because it's alphabetically, and that's how I've ordered your submissions, how I've ordered the slide you've sent me. So first we'll have Yasin, Kaylee, and so on. Yeah, so if you want to know when you go, I'll show it during the break as well, so you can get ready for your own speaking time. And today, however, I'll go back to duplicating the screen. So today we'll be talking about vectors. But before anything, I have again some administration things we need to share. So I've already mentioned assignment 4. So for those of you who have not emailed me until late last night, then you are not able, or maybe I should start with assignment 1, that's true. So with assignment 1, if you don't have an access to Esri, ESRI online tutorial, send me an email and I'll immediately send you the link. If you won't do that, you're not able to complete assignment 1. Is there anybody who still doesn't have an access to S3 tutorials? Good. So if you know somebody who doesn't, tell them to send me an email. Yeah? Assignment 4, as I said, the enrollment for week 1 is over. Even the enrollment, extended enrollment, because we have so many newcomers to this class who could have signed until the end of week 2. So if you have not signed in or haven't emailed me, you're not being accepted to actually do the assignment 4 at all. Assignment 2, we're already in round 2 this week. So last week you did the module 1. This week we're doing the module 2. So if you have any questions, ask the demonstrators, the tutors you have in your lab. That's why they're there. So make a use of them. They're really experienced in what they're doing. Somebody asked me about deadlines with submission. You can submit later, but there will be penalties. The penalties are a certain percentage of the maximum points you can get. And then it varies if it's within the day, within the same day, within 1 hour, or if it's the next day, the day later, and so on. So be aware of that. And if there's a deadline by 9 p.m. or 6 p.m., make sure you stick to that. If there is a problem with LMS, then make a print screen while it's happening. Do some, make a proof that you can show me that you had the problem, and this late submission can be annulled, but you have to prove it somehow that something was happening, or ask university services that you were, show me a correspondence with them that you were trying to solve a problem you had with the software or with the network. Or if it was on your side, like your home connection was out or something, if you have some kind of a proof, please put that in an email so we can take that into account. But generally, just submit things on time. In week 7, that's in 4 weeks time, we're in week 3, we'll write a mid-semester test. It will typically be multi-answer questions, A, B, C, D. I'll ask for some definitions or explanations of some questions, and you might be asked to calculate something. So last week, There were a few calculations this week. There will be some more. Not too difficult. The basic principles, the fundamentals. So keep that in mind. If you want to look at the samples from last year's, there's plenty of them on LMS. Does anybody have any questions to admin? Yes, Alex. No, for assignment 3, that's true. There's no information yet. It will be released later. You'll get information just on time, but don't worry about assignment 3 for now. You'll have plenty of time, plenty of things to do with assignment 1 and 2. We might release it in a couple of weeks' time. Any other questions? Okay. Then the next slide. I've noticed, based on your questions at the end of the lecture last week, there's still some confusion with projections and reference systems and so on. So if you look at this scheme, I made it a little bit more complex, but hopefully it will make it easier for you to understand. So at the top we have the Earth's surface. So that's the topology, oceans, and everything together which exists on our Earth. If we simplify that, if we take out the topology and oceans, we get a shape that is called geoid. This is still within the 3D thinking. To position ourselves on geoid, we use something which we call the reference system. Generally, we use ellipsoid. That's the best approximation of the geoid. Are you with me for now? So we're simplifying the geoid to ellipsoids, to fit it somehow to the surface. And examples of ellipsoids can be the GDA 94, the Geocentric Datum of Australia, or GPS system, the system that uses GPS, WGS 84. So these are the examples of ellipsoid. Generally, they would use the phi and lambda, latitude and longitude, the parameters of two radiuses. See, there's like my arrow kind of went over the bracket. We can also simplify the geoid even more. We can use sphere, which is easier for calculations. We have only one radius to define it. However, it's already skewed. It's not that correct as ellipsoid. Yeah? And this is while we're still simplifying the Earth's surface in 3D. That's what we call the reference system. So most commonly we use ellipsoid reference system. WGS, GDA, so many more. They would use latitude, longitude. Yeah? 3D. Then we project those 3D objects onto a 2D plane. And that's when we have the projections. That's peeling the orange, making the 3D appear on 2D, either on a screen or on a map. Yeah? Are you with me?
Is that a rectification process? Or
Pardon?
is that to project
From 3D?
from the sphere or whatever, or the ellipsoid to the map itself, to the 2D? You do rectification?
That's a rectification.
What is the difference between projection
and rectification? Rectification is putting an image or a map to a correct reference system. For example,
but when you do that, actually you are projecting.
yes, the word project can be used for many ways. So for example, last week when we talked about rasters, you could have a raster image, which is a central projection, and you know that the edges of the raster is skewed. So if you don't want your raster image to be skewed on the edges, you do something which is called georeferencing or rectification. So you make sure that the cells of the raster are correct within the selected coordinate system. So that would be the rectification. But it's a rectification of an image of an existing map to a specific reference system which you want to use. This is going from 3D to 2D. It's not exactly rectification.
For me, it's like a same because you already have the coordinates, but you have it like with different problems. I mean, like probably tilted or some part of the image or whatever.
Well, you have it for the 3D shape. You have the coordinates on ellipsoid. You're not yet using the Cartesian coordinates of the 2D paper. So on 2D you can have just x, y, simple Cartesian. But the phi and lambda, it's on the ellipsoid. So these are, we both call it coordinates. That's why it gets confusing. But phi and lambda are coordinates on the ellipsoid. And then you can have Cartesian coordinates, x and y values, some system.
The projection is a step.
The projecting is a step from 3D to 2D when you peel the orange and make it flat on a paper.
Yeah.
That's what we call projecting. And then the function, the formula behind this peeling of the orange, behind this going from 3D to 2D, is the projection. Yeah.
So just to confirm two
Yeah.
points that you raised, the reference systems are particularly the forms we're using from 3D to project into 2D. So
No.
sorry,
Reference system is the 3D. If somebody ever talks about the reference system, they usually refer to the 3D. In literature, it can be confusing, but I will try to use reference. Whenever I say reference system, I use the 3D ellipsoid reference system. Because this reference system, I can then project into different types of map projections.
is there any other, just curious, kind of reference system besides the ellipsoid and sphere used for the other? Is this pretty much it? Like,
Well, if you combine multiple, you can have like a hyperbolic space, for example, but we don't need to simplify our Earth into hyperbolic space because it's more or less round or in the ellipsoid shape. But that would be like a different mathematical space. That's what you mean. What do you mean?
And the second thing I wanted to just confirm was that the projection that you've done from 3D to 2D in the ellipsoid over there,
Yeah.
can we safely say that that's a shape conformal projection?
No.
Versus the one over, that's a shape.
You can't safely say, you cannot say that if I'm projecting anything from ellipsoid, it's conformal. It depends on the projection, on the function of the projection.
Well, but
It can be different things. However, what you can say is you can see, if I'm projecting from sphere, which is already skewed, it will never have any of the true projection properties. It will never be equidistant, equivalent, or conformal, because I'm using a globe. It's already skewed. It's more precise from ellipsoids. From ellipsoid, I can get conformal, equidistant, or equivalent map projections. But it depends on the projection.
But just like if we take out the maps and just look at the shape
Yeah.
of both the maps, can I safely say then, given that caveat point out that projection
So if this is both Mercator projection, and this one is made from ellipsoid, so this one would be Mercator, this one, yes, this one would be conformal. But if it's a Mercator done from the sphere, it's not conformal. So as an example, the UTM, the Universal Transverse Mercator, yes. However, Google Maps, even though it also uses Mercator projection function, it's not conformal because it's using this. It's coming from a sphere. Is this clear? Okay. Good.
Can you not clear the arrows? Saying transformation.
The transformation. So we can still do a transformation in between. I can go from ellipsoid to sphere. I can go from this map projection to this kind of projection. So this is some calculation behind if I'm going from one.
I can go directly to the sphere and give coordinates to the sphere.
You can go directly, but you will have some coefficient, some function again behind how you're changing into a sphere. Maybe like you're making 2 times smaller and +5 or something. I don't know. That's your added algorithm to this projection. You're adding another part of calculation. That's what we call the transformation. Another mathematical operation behind the two different shapes.
But I mean, you create ellipsoid. As you
Yeah.
create ellipsoid, you
Yeah.
can create a sphere.
You create it, but they don't have the same mathematical functions. They're not defined the same mathematically. So the difference in between, if you know what's the mathematical difference in between, you can use that to transfer in between one of those. But you would have to use this definition that defines the difference. So that's what's called the transformation. Okay. So today's topic, we'll start talking about vectors, and more specifically their nature, representation, and visualization. So nature and representation of vectors. What are vectors? I'm sure you've come across that in, I don't know, physics or math. So vectors, vector representations are data that are based on points, lines, or sequences of lines. So if we have a sequence of points, we can say 2 points, if we connect them, there's a line. If we have a sequence of lines, we can create a polyline, or we can create a polygon or area. So we create something which we call multi-points, multi-lines, or multi-areas. So polygons and polylines are features that consist of multiple line segments. So this can be a polygon, so you can see it has 4 line segments. Just a note why that curved shape is crossed. In GIS and spatial systems, we don't use curved lines as opposed to construction or any technical drawing. I know it looks nice if you can define a curve, but with GIS system we don't at all use curves, and mainly to simplify the calculations. It may look nice, but it might be not as practical for doing robust calculations. So how are they defined? Point, lines, and polygons, we can call them as simple features. So point is represented by 2 coordinates. Just some example, easting, northing, Cartesian, x and y, or phi, lambda, latitude, longitude. Just one point is defined by giving it 2 coordinates, x and y. Yeah? Lines or a linear segment are represented by 2 points that are connected. So this line L is a point 1 and point 2. And then we can have polygons or polylines. So polygon is a closed polyline, and polyline is an open polyline. So polygons are represented by a sequence of lines. So we have 4 lines under the conditions that if this is my P1, this is a P2, like point 1, point 2. The point 2 is the start of the next line segment. Sure you can all see that. And also the fact that it's closed at the point 1, the last line segment has to end in the point 1. If it's not closed, then it's not a polygon. It's just a polyline. We do use polylines and polygons as well.
So if it's closed, you have 5 points.
Pardon?
So if it's closed, you have 5 points.
It can have as many points as you want. In this case, this is, no, it still has 4 points. Just the first and last segment, they share the point. So the point 1 is a start point for the line segment 1, and end point for the line segment 4. So it's still 4 points.
So
We're not counting the point twice.
Okay. So it's actually defining metadata elsewhere whether it's closed or...
Yes, yeah. Or like when you have it, for example, like in ArcMap, it's just as a series. It's a list of coordinates, and the last one for the last point, it's like it comes as an array, would be the same as the first coordinate of the first point. So that's how you know that you're drawing it together. But it's because it's within the same array, it just shows as one feature.
Okay, so the last point is the exact same.
Yes,
as
yeah.
the first point.
Yes.
So in the example on the projector, so
Yeah.
it will be the first point going around, the last point will be the first point again, but that's the 5th point of the array.
In this, okay, what I've explained, but there's a different ways how we can store the vector data. So in this case, yes, but we can store them differently in a database, so it can be defined other ways. But in this case, yes, there would be 5 points written, like 5 sets of coordinates written, and the first one and last one would be identical. But we can have other ways how to store the vector data information where it may not be true. So don't take that this is just forever.
So
This
it
is the
also
old.
depends on the database.
It will depend on the definition of the database, yes.
Usually we have like points, lines, and polygons.
Yeah, we can simplify that differently, yeah.
So
It's
are
like
we
the
gonna use
spaghetti
this-
data model and those.
Are we gonna use this like polylines and lines? We wanna to describe them like this way.
Yes, if you want to use this example, yeah. You had it.
I have the same thing. Like in this particular example, we have G is equal to L1, L2, L3, L4, and L1. If we want to make a polygon,
Yeah.
and this particular thing represents the polyline in this example.
In this example, well, there will be somewhere in a database a note that this is inside or outside a certain feature. So it can be a polyline or it can be polygon. It can be a closed polyline, that's true, but it can be a polygon if you have somewhere in a database information that this area that is closed by this polyline has some other qualities that you want to separate it from the rest. That's how you would then say that's a polygon.
So basically there can be in the database, there can be an attribute. Like this is one of the ways. Second way can be, there will be an attribute which will say this thing, like it will be ticked or like unchecked or checked. It will say it's a polygon or a polyline for the same vector.
Yeah. It would depend on how we store it. Okay, there's a question that the points and lines are not represented. And I need to go in our pool. So why do you think the points and lines are not represented? Like how everybody's waiting for the answer. So think, why can we have just a start and end point? Why don't we store in database every single point there is? Is this all of your answers? More of you wants to answer or change their answer? Okay, the B is growing. That's good. Because this would probably be the main reason, B, that there is too many of them. If it's a line and from math, as you know, all points and lines, there's technically so many of them. Now there is an infinity number of points there can be on a line, so you actually don't want to have all of them. And because there's too many of them as well, if we can define lines just by connecting point A and B, they are as well redundant. So the first two answers would be the correct ones. The fact that we are not representing any points inside a polygon is more of a joke, but it's true as well. So basically good thinking, everyone who voted. Okay, vectors. How do we represent vectors in our reality? Similarly as last week with rasters, imagine that this image on your left is a continuous representation of our world, and we can represent it using points, polygons, and polylines. So you see the points are those squares that are connecting segments of both the lake and the road. So this line segment is the road, and the blue segment would be the lake. So it's line segment for road and polygon segment for the lake. So it's a closed polygon, and it's colored blue, which reminds us of water. And the main difference between raster and vector is that you can put the point anywhere. You're not bound to a specific grid cell, a specific grid boundary. You can literally put the point anywhere you think. with whatever precision you want, yes.
A particular red will have two polygons, say that one will have two parts without one.
Well, it actually looks like it's too late, that there is a land underneath this road. There's like probably a dam built. It's not the best image for it, but it may be just a bridge, but it actually may be split in half. I don't know, I haven't been there. It's from a textbook. So what I see, bridge wouldn't be this wide, can be, but I guess maybe it's not. So it might actually be divided in two. If it wasn't, you would connect this polygon underneath, and that wouldn't be wide. It would be all connected with one polygon overlaid with the road.
Yeah, now see if you're interested, say suburb might have two parts.
Yes, yeah, that can be. Yeah, but I think this leg is actually divided on the image. So when we vectorize, we create something what we call the well-formed geometries. Some rules is that polylines are always connected, and polylines do not self-intersect. So basic topology rules which keep that in mind, otherwise it will mess up with all of your analysis. Same goes for polygons that they are always closed, and that the boundaries of polygons do not self-intersect. So it's good to store them. They're formulated as some database rules, and again, then it depends on what kind of data storage we decide to have for our vector data.
What does it mean that boundaries of polygons are not self-intersect? I can't particularly visualize it. Is that from a database perspective?
Similarly, like if you have 2 points crossing, 2 lines crossing, you do not want 2 polygons within the same layer to overcross. If it's in the same layer, you want them to be that where one ends, another starts. If it would be 2 different layers, then it can happen. But if it's within the same layer, you see this is polygon 1, this is the border of polygon 2, and then polygon 2 would be just below. It wouldn't have a different border.
Oh, so they can't overlap at all?
Yeah. Yes.
It
No.
has to be a separate layer.
Yes. And there's a...
For example, in roads, you have a road that is stick.
Yeah, if it's a road...
At the same height, it's basically the same. It's polylines. You're using polylines.
Yeah.
You need them to intersect.
Yes, with roads, that's a good example. Yes, with roads, if the road intersects, it physically really there's an intersection, you need to create a point where the roads intersect. However, for example, with a level crossing, we have a line of a road, or even still you have a road underneath, road over, there's a highway. They can be in the same layer, and if they do not, they can intersect. They can go over, but they would actually mean that there is a bridge, that this road goes over, that you can't turn onto this road underneath because you're above that, for example. So that's why it's important to keep the topology correct, yes?
And in that situation, would you then probably separate the layers, for example?
Ideally, you would have them in different layers. Yeah, but it can happen you have them in the same one, but you would have some line attributes that they have different properties. That is a different layer.
Would a polygon and polyline intersect?
You wouldn't have polygon and polyline in the same layer ever in GIS definition, so that wouldn't be a problem. You either have a polygon layer or polyline. So if it's a different layer, you can do calculations with that. Just some mathematics behind it. Something which is called Jordan's curve theorem. I know it says curve and I said no curves, so no curves. This is just how Jordan called it. It means that a simple closed shape, let's say, simple closed curve separates an interior from the exterior. It means that one line segment of a polygon separates the inside of the polygon from the outside. That's what this Jordan's curve theorem means. Then only one line separates inside from the outside. Yeah, keep that in mind. It'll play a role later today.
What is that graphically? What do you mean? Polygon is a polygon if all the lines are closing together. If one line is removed,
Yeah, I have some graphical examples now, so let's think about it now. So are these well-formed geometries? Think about the first example. What is it? It's written there, it's simple polyline. Is it correct? Yeah. How about the second? Because they are overlapping, yes, there is no point in between. What's the second? The third one? Again, it's a simple closed polyline. Is that correct? Yeah. Can it become a polygon if I would say that there is something inside? Yeah. Yes, true. And the last polyline, this one? What do you think? Yeah, it's a polyline, but it's not closed, so it cannot ever become polygon. Couple examples of polygons. Polygon and a convex polygon. It's good to differentiate between convex and concave polygons. This one would be a concave because this angle within this polygon is bigger than 180 degrees. That's when it can become a concave.
You said something about polyline being closed or not. Are polylines just by nature supposed to always be open? From what I understand, polylines, I don't understand exactly, but polylines are always open because they always have.
It depends what you're representing. By nature, polyline doesn't always have to be a polygon. Imagine you're mapping, I don't know, an athletic stadium, and you want to map the running track around. So you want to map it only as a line, and you want it to finish and start and end at the same point. So you will map it as a line feature, as a closed polyline. But what's inside this running track is actually not part of the running track, so you would not define it as a polygon. You would keep it as a...
So that's the case of a closed polyline.
Yeah, that would be a case for a closed polyline, yeah.
Okay, and open and closed, the concept is more to do with like how you're measuring the variables you're trying to represent.
Yeah.
So the polyline is literally points on the line.
It's,
Polygon,
yes.
if we're
Yeah,
looking at
polygon,
within the
if something is within this boundary, yes.
Right. Okay.
If I'm interested what's inside this field, then that would be a polygon. If I really want to know that this is running track around, that's a polyline.
So does that mean that closed polygons can also be considered closed polylines?
Yes, under certain conditions, yes. If you don't care what's inside, you just want to know the boundary, yeah. Or like country, boundaries of a country. If you're interested purely in just the boundary, you can use them as a polyline. If you want to know this is where, I don't know, this is where Germany is, this is where France is, you want to know what's inside this boundary, then you would talk about polygons. So there's some fixing. So ideally we will add a point in here to fix this polyline. It's just a note that this is not a closed polyline, that's almost closed polyline. How do we map using vector? So imagine you need to vectorize a section of a highway. This is on Eastern Freeway. How would you do it? Using a vector representation. You have a couple options. So first thing you can do, you can use center line. So it can be used for mapping on a small scale where you really want to know where is actually this highway located. You can draw the line in the center. So if this whole thing is a highway, we can draw a line right in the center. The same would go for the connecting exits and runways. So it gives us information of the location. However, you can see it's already lacking some detail. We wouldn't necessarily want the car to drive along this red line, because it would be driving in the middle, in the grass. So it's already lacking some information. But this is definitely one way how we can show features we have using vectors. So using more detailed representation can be drawing the carriageways. So if I know I'm driving in this direction, I can draw a line going that way and another down, same with the exiting ramps. If I want to go into even more detail, I can create a vector line representation for every lane there is. So if there is, I don't know, 3 or 4 lanes, I can have 4 vector lines next to each other showing me the lanes. So I'm increasing the detail. I can still use vector for that. Or maybe I'm interested in the space this highway takes in the parcel, so I can map it as a polygon. I can just take out this shape, and on this land there is a highway. So I can use a polygon to show that.
Just to confirm the first one that we saw about the center line, if you could go back to that. In the center line one, what did you say was the richness of the data being used here in the one point, the center line? What did you say was the utility for this?
Location.
So,
This is showing us the location. If my map is, let's say, quite zoomed out, I don't need to distinguish how many lanes or carriageways there is. I'm purely interested, this is where the highway is. We can maybe then distinguish, notice that this line is thicker, so we can then distinguish that this is the highway, these would be the connecting ramps, so they have less of a priority. So that's what you can do when you're mapping this highway using vector.
so
Yep.
another representation be, for example, that we use the middle line to give us perspective on how far each lane is from one another, and then how we can adjust our freeway exits accordingly.
Yes, yeah.
Or if
This is if you're doing some modeling, some analysis, and you want to have a very precise data of your highway, you would do something like this. You would add in more information, but as you can see, if you're the one who's vectorizing it, it needs more clicking, it's more work, it's more comprehensive. So this one would be more detailed. And the third one, I can just look at the parcel this road occupies from a, for example, urban planning perspective. So these are 3 very different representations using vectors. And so you can see that vector geometry is a tool. But it's up to us to decide which way we want to represent what we are trying to map. If I'm only interested in location and some basic calculations, or if I want to know very detailed how many lanes there is, very detailed description, or if I'm interested in the shape, in the size, in a parcel, if I want to calculate areas. So it's us who have to decide which way we will represent the reality using vectors. So another example is using points. Points are very, very commonly used in mapping. For example, we are mapping addresses. So points are everywhere. We use them for general location. So imagine some postal services, they are not interested in the size of the parcel your home lives in. They don't need to know where exactly it would be a center point of your parcel. They just want to know where is the location where they need to deliver a certain thing. And other examples could be some geographic features or geonames. If you want to place a label onto a specific feature, you want to find the centroid of this feature where you would label it. So in the very center of that feature. That's again, you would approximate a center from a polygon feature. Or if you search for a city on Wikipedia, it will give you a coordinate. If you search for Melbourne, it will give you one coordinate. But you know Melbourne is bigger. It doesn't sit in just one coordinate. So it will give you the center point of Melbourne, which is, again, it's a point. But if I'm zooming out, if it's a map of a small scale, looking at a Melbourne, I can use only point representation. However, there are some problems. Okay, there is a note that in Victoria, what they're using, that the point for your address is about 3 meters inside from the parcel front. So if this is a road, I know this is a parcel front, so the point would be located about 3 meters inside. However, that's how it's defined here in Victoria. It can be defined differently in other locations, but it comes with problems. So what if the entrance is somewhere else? What if this is the parcel front, but my entrance is from a side? How would they know where to deliver it? Or also, what if the parcel has multiple entrances, or it's very large? So it's not a perfect system, but it's a pretty good one for what we need to do with postal services here in Victoria. It can be used for logistics, population statistics, general delivering. You can use as a single point representation. We're using the fact that we can approximate in our minds that it probably refers to something bigger, that it's not just that one point. We can also use points to represent geographic fields. Fields within, let's say, a bigger area. So it would be observations. We can measure some observations within a specific field. Let's say I'm talking about a temperature. So I have meteorological stations randomly scattered around the space, and these would be their locations. This is the coordinate of each of the meteorological station, and I'm measuring temperature on each one of them. So just to show some continuous information, we can use vector geometries using point geometries for fields. And what we can do afterwards, we can interpolate. Another interpolation, not like in raster. So imagine in some of these corners, I've measured certain feature. In this case, it's the surface height. So I've measured the height here, 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 here. In some of those corners, the points are not very visible here, but imagine that's where I've measured them. And then I want to interpolate the surface height in between those points. So I will take all of those points into account within the field, process it with an algorithm to interpolate the differences. So if it's a contour line, like this one, it can be called isohips, but generally we would say isoline. There's many interpolations techniques that can do this. Different approach to measure different height along the fields. So another very commonly used representation of vector data is something called triangulation. And it's partitioning the Earth's surface into triangles. So if I'll go back, imagine this is the Earth's surface, and I've measured points here, 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 and here. So I can connect them in a triangular way for so-called triangulation. So similar like with rasters, but this is with vectors. I'm partitioning the surface into triangles. They are of an irregular shape, as opposed to rasters. They're never the same. Usually you can say this triangle is different than this one. Very irregular. I'm literally connecting every point there is into triangles. Okay, they're irregular because the points I've measured them are in an irregular manner. If I would measure the points in a very regular manner, they can be more regular, these triangles. But generally, I'm not able to have them precisely every point 1 meter aside, for example.
Why do they use, just like rasters use grids, why is triangle being used, or is there a particular incentive, some sort of benefit to representing it triangles? Because this is like the question that the rasters want to do.
Triangulation was here historically before rasters, let's say. Rasters, the benefits of a raster to store surface height would be that it's, well, it depends on the size, but it can be easier to calculate things with rasters as well. And triangulation, I'm sure even like if you go outside, you would see triangulation points. Even in our countryside, so you can measure from one triangulation point distance to another. So you can map that just using a vector without having the computer-based software for that, which you were not allowed to do, which you can't do with rasters. Rasters have to have some computer processing behind it so we can actually work with it. But with triangulation, or you could, I don't know, you could use a square paper, but it seems like a lot of work. But with the triangulation, it's mathematically easier to create. And we had triangulation before rasters.
Do you feel it's more the ease of calculation or more just that it's historically just been there, so it's a more popular reference system?
Neither. In my experience, I'm switching between raster to triangulation, and I get a triangulation field, I immediately convert it to raster. It depends what you want to do with your data set. What's the purpose? Everything has its benefits. You can, I don't know.
What do you forego when using triangulation versus using a raster representation of the exact same, like the raster grid system of the exact same thing?
To create a raster, you would create a raster probably from some triangulations. So triangulation will be first because you measure things somewhere, the location somewhere outside, unless you measure them from a satellite image. It's just the rasters produce differently. Let's say if it would be terrain height from satellite image, that would be a raster. If I'm measuring terrain height on the Earth's surface, I would use triangulation. And then I can then convert it to raster as well. But the benefits of using triangulation is, for using 3 points, so it's the most effective way to show the surface because you can already see the surface, just how it's connected, you can see the surface as it is. So trying to point out there's a mistake, there should be a line. Somebody made a wrong picture. And another benefit of triangles is that they are always, now I'm confused, it's concave on convex. Yeah, they're always convex. Yes, sorry, I don't want to say the wrong word. So triangles are always convex, and they're always on a 2D plane. 3 points, if you connect 3 points, they still have to be on 2D plane. There is no other skewing you can have with them. Yeah, that's why it's the main benefit of triangles. They're convex, and they're always on a 2D plane. They're very linear. Another question before we have the break, and I need to do this, still haven't fixed it, I'm sorry. So what are the benefits of a contour line representation of geographic field? The contour line. Any more answers coming? Although both answers are right, the visual analysis of the field is the main reason why we want to use contour lines. Because if we have just, if I go back to presentation, because if you have just points, It doesn't tell us much about the field, about what's going on. It's still points. But if we connect them in a certain way, then we can have a better understanding of what they try to show us. However, saying that it's also good for calculations, because doing the interpolation, having the contour line, I can approximate the value which is here, here, and here. So I can have more, I can produce more calculation results. Okay, we can have a break for, I don't know, 5-10 minutes. And in the meantime, I'll put up the list of today's presenters. So that's the order. Hopefully I've ordered it correctly, so I have your slides here in one PDF in the order I've shown. Yep. So we'll start with Yassin Ali, continue to Kaylee Beer, Alex, Karan, and so on. But let's have 5 to 10 minutes break. Have you done any RGIs? Have you done the Esri assignment 1 tutorial? Have you noticed how you have different layers when you show them? You would have like a layer of road, layer of schools, layer of different things. So that's what I mean by different layer. So if I'm showing, I don't know, let's go a little further from the recording so we can. I'm showing the road. I will then show down that one layer of jungle, and then I also have a layer of buildings. So in the layer of buildings, in reality, I don't have two buildings kind of like really connected to each other. So you want them at where one building ends, that's where another starts. You want them to keep it as close to mention that Sebastian, not Stefan, Mr. Sebastian, will present first because so will be some changes with them. What's the time? Okay, we still have a few minutes, so you can get ready. Let's just put your presentation up first then. You like at the end now?
Yeah, that's me.
This is yours.
The red one.
This one.
Which one's that?
You're pressing the down. Yeah. Okay. But it's number 8. We'll start with you and then we'll go back from the beginning and then we'll skip you again. Okay, I'll get out my phone because I'll be measuring it.
Yeah.
Are you happy to start?
Yeah.
You can make it full screen.
That's fine.
I'm gonna make it full screen. No? We can start with our assignment 4 presentations. The first one is Sebastian. Do I say your name right?
Yeah.
Okay, so you can go.
So this is a map from the article titled Pakistan Downgrades Diplomatic Ties and Suspends Trade with India over Kashmir. Doesn't get off to a great start. It's missing a couple of basic features like the title, legend, spatial reference system and production information. This makes it difficult to start to establish the credibility of the map. There's also a number of things that lead to a bit of a biased map. The first one is the colours used. There's no actual reason to have colours in this map as it's not showing extra data, and the red implies aggression, whereas like yellow is traditionally a more neutral colour. Combined with the title, this suggests bias as Pakistan is like being the aggressor is what it suggests. The other significant problem is there's no reference to the border data used, and this is about a disputed border. So the data source will lead to a very different map. For example, an Indian map wouldn't show the Pakistani-controlled portion of Kashmir. In combination, these lead to a bit of a biased map.
You can finish the sentence.
That's it.
Okay. Well done. Thank you. Now we go back to the beginning.
Yeah.
So then we have Yassin.
Good afternoon, everyone. So the article I chose was published on The Sun. It talks about the UK's Prime Minister has given the green light to 20 new buildings and infrastructure projects in the National Health Service in England. The article I chose has a map showing the locations of these hospitals across England, followed by a table with the names of these hospitals and how much each one will be getting. Map analysis. The geographical information presented in the article itself was designed by The Sun, a publication themselves, as I haven't found it on any other article that shared the same news. It has good colors, but it's missing information as all the pins means nothing without looking at the table, right? Recommendations. It could have used more info like the date to be present on the map and adding a watermark for the audience to know that it only belongs to this publication. It could have also, I'll just go really quickly. It could have also been zoomed out map with locations having the lines plotted out on the side with additional information mentioned in the table. Also, there was a typo in the title there that needs to be fixed. Okay, thank you.
Okay, so it's a little small on the screen, but it was fuzzy in the article too, so yeah. I found this image on the article, Geelong Real Estate Hotspot Revealed as CoreLogic Launches Mapping the Market Tool by Peter Farrago. So those are Geelong suburbs. They're looking at the real estate value of average of each suburb as it changed from 2014 to 2019, but you can't really tell that from the image as it doesn't contain like a title or a legend or a scale or anything like that. It does have some information in the article about what the colours mean. So the lighter colours are a lower value and the higher colours are a higher value, but they don't have any sort of number associated with that or anything that will tell you what the actual value is. So the CoreLogic is a company that I'm not sure who contacted it because this article is also republished in another website, but it's behind the paywall. So, yep.
Yeah, thank you. Did they really use just that image? Just that?
That's the caption. There's another one from 2014.
I'm looking forward to read about it. Thank you. Another one.
Okay, so the article I was looking at had this geographic illustration that shows the percentage change in the drug seizures in the Southeast Asian countries here between 2014 and 2019. I think it was quite a good map to like affect the way to visualize like the drug problems that is in Southeast Asia, but I have some major issues with the actual performance of the map. Like it's a bit messy. You can see there's a lot of line boxes and percentage, and you don't really get a good grasp of about what it's actually trying to say. And also there's some problem with like the basic map structure. For instance, like where is the north arrow? Where is the scale? Like and also the label. For instance, where's that yellow triangle? Like what? And then the yellow triangle, and then it's not explained. Okay, yeah. Thank you.
Okay, hi. So this was an article which was published last week based on a research paper that has been published on the 29th of July. So basically, researchers have found new ways of how to calculate the velocity of ice that is flowing from the Antarctic into the oceans. So as we know, the Antarctic gets a lot of snowfall and it releases a lot of its snow or water into the oceans, which contribute to global sea level, ocean level rising. So basically, what this map has been able to do is get the accuracy very high, telling us better predictions for water level rising. Coming to the map itself, well, it's fairly well presented because it's showing only the geographic location that it's supposed to, that is Antarctica. It's not shown any other features, it's just sticking to what is required here. It's given a proper scale, it's color-coded the velocity. The colors are not very accurately done, but they are doing a decent job considering the different colors here. And well, for missing parts, it's missing a compass, even though it's pretty obvious that it's pointing towards the north, but it's still missing a compass.
Do you know why it's missing a compass in Antarctica?
Doesn't need.
Everywhere you go from Antarctica.
Yeah, pretty much, yeah. And well,
It shouldn't even have it, but it's good.
yeah.
It's not a compass.
The name down there is basically of the author of the research paper, but the research paper itself does not contain the map, so the name down there is from the source. It's a little questionable. And well, that's it. It's missing the projection and datum details. Yeah.
So next we have this map from Tasia. Thank you. I'm Laura, that's the name of the author from the article. I didn't put my name on it. So this article was for major peak hour traffic delays in Sydney CBD. The map itself was actually just a screenshot from another website. So there was a couple issues with the design of this map. So obviously it lacked a lot of design elements like a scale bar, legend, and north arrow. So that makes it difficult to understand the map if you don't know the geography of Sydney already. It also used distracting and irrelevant symbology. So the only symbol that was actually relevant to the article was this very lower exclamation point. All the other ones were not mentioned at all, wasn't relevant. Third thing was there were very poor referencing. The only reference to the actual source of the map was in the caption, and it just said live traffic. And then finally, the source of the map data itself was from CCTV cameras, public reports of traffic incidents, and Google Maps. So all of these different sources have their own inherent biases associated with them.
Hi everyone. So this article was published by Vox News, which is an American news media company, and it was a contribution to the long-standing debate on gun control in America, particularly with the rising gun violence. Now, I feel as an introduction piece, this does a great job as a map. First of all, you see the shape-conforming structure and the fact that the scale is very intuitive, from a lighter color to a darker color, showing the intensity in different states where it's a bigger issue. And finally, the fact that they added a shaded effect to show states with tighter gun control equals less gun violence. For any person who comes in who wants to get an introduction to the issue on how bad gun violence is in America, they can look at the map and say, you know what, that tells us a lot, that tells me a lot, and they could get interested in it. So it achieves that objective. The cons, although not that many, there are a few small caveats. One of the things is that the scale, while choosing a 5-5 step counter, doesn't intuitively show that the lowest death count is 2.4 rather than 0. So some yellow states could be mistaken as having 0 gun violence. Alaska and Hawaii are not here. So for a millennial like me who doesn't know much about like places or what countries are, this is a bit inaccurate, but space limitations. And finally, data is a bit outdated. For example, for a 2019 article, you shouldn't be using data from 2007. Sure, it tells the intensity and severity of the topic, but a bit of an issue there. That's it. Okay.
Next we have Britain.
Hello everyone. So this is a map I found on the Sun newspaper website, and it shows where burdens, high assurance, live place. The data is from the Institute of the Physical Studies, and I found the good thing is that they use the constituency in true shape instead of the polygons in original data. But because of that, so you can see it's covered by white dots, so you can't really see the true color of London, which shows the majority of the 1% cup. And another thing is that the map didn't show the Northern Ireland, but it says live in UK, so it's kind of problem that cut off the map from that side. But from original data, it said it will go with the notes that the North Ireland didn't include in the database. And final things is that the color, they use the color from dark to light, but we tend to think that the dark is the population higher, light is lower, so it's confusing. Thank you.
Then we already had that one. Another one.
Hi everyone, so I found this map. This is like a supporting map to a newspaper article. So basically it has the essential elements because you can see a title. So like it shows the dots cities with 5G capabilities in the States. So like the colors, the balance, like it's very easy to see. It's overall it's very simple for visualization. However, so for someone who's very unfamiliar with the States, I wouldn't know which parts, like what are the cities. So like only those in those who stays in the States, they would know like, oh, these are where are the cities. So I feel that is pretty lacking. And also like not to say there's no scale or know nothing. So, but I do think it's nicely referenced with the sources and the graphics, but I think generally it's just to use to support the article, because the article is the main point at the moment. Yeah.
So hi everyone, this is the graphic from news talks about the Great Wellington Regional Council's release of the Climate Change Vulnerability Report. So the left graph is the original graph from the report, which is available online, and the red one with the caption is the actual graph they use in the news article. So we can see like they just simply chop off some less important part of the graph and put it in the article, so it can make the audience think like, oh, this oh, my home is in this part, and it's really valuable to the sea level rising. Oh, that's a little bit crap. So, cause like in New Zealand, like we really do know, like we suffer from quite a lot of types of the natural disaster, like earthquake or storm, something like that. So this just simply make people raise the awareness of the sea level rising will do affect their home or working space or something like that. Also, it encourages city council to do something to face this situation, so can get some time to do something. So I think that's it. Thanks a lot.
Thank you to all presenters. I think we had very interesting examples, definitely. Sometimes I'm very surprised with everything you can find in the news, with many, many mistakes. But let's move on with our lecture. We'll do some basic algorithms, some calculations. So what is an algorithm? I'm sure you've all heard that word. It's a set of rules that are specific for some kind of calculations. So algorithms is a set of rules. And it has some properties that we should follow. Their correctness, efficiency, and robustness. Correctness, it's on a first place because of course we want our algorithm to be correct. To know that it's correct, we do some testing, we need some proof that it's correct, that it's calculating the things correctly. But please know that it's quite hard for geographic data to prove that the algorithms we use on them are correct, mainly because of how many geographic data we have. Another property is efficiency. It's typically measured using something called the big O notation, which shows the order of complexity. It's an exponent only, and shows us typically the worst case scenario that if our algorithm is too complex, it will have a high exponent. So for example, if we need to sort 10 points, it will depend on n times. We have 10 points, mean n records, so it will depend on n times. I would have to do the algorithms on n different points. I hope I'm saying it correctly. So I have 10 points, and the algorithm will need to run for each one of these points, so it will be n times, n 10 times. The n will be 10, so 10 times. Oh, do you get it? Thank you. Hopefully. Another important property is robustness, that we want our algorithm to work in all conditions, which means it's not working only on Monday at 7 a.m., that whatever kind of data I can process, whatever amount, small or big, with various different attributes, it will still work. Right? So it operates only under most circumstances. There's an example, it's more of a story, but it was a paper by David Douglas. Then he was a professor who approached students and asked them to do a job for him. He gave them a choice that they can either get $100 for creating an algorithm, or they can be paid by an hour. But they had to make a choice. What he asked of them was to create an algorithm that will tell if two line segments in a plane cross each other. And if they do, so it can return the point where they cross. Do you think it's simple? Have an algorithm that can tell us that two lines cross each other, and if they do, tell us the point where they do cross. Fun? Yeah. So it should be simple. We would expect any GIS software immediately be able to do that. It should be following some basic geometries. But the fact that he already asked somebody to do that algorithm for him should make us cautious that it probably has some downsides to that. And he was, as the title said, it made him so cross. So what made him so cross? How do we know that two lines cross? If we look at the first blue example, that's quite obvious. They do cross. No questions with that. What do you think with the green one? Do these lines cross? Okay, the line segments do not cross. But if we would continue the line on which this line segment, the bottom one is, it would potentially cross. So we would have to define that it's just a line segment, not a full line on a whole plane. How about this? Is this a cross or not? Who thinks it's a crossing? Do you think it's a crossing? Do these two lines cross? Let's vote. Who thinks it's crossing? Okay, who thinks it's not crossing? See, you have to define these things. Yeah. So it's showing how complex of a question that already is. There's a set of rules that we have to define, and they depend on us, what we need to find. We need to decide if this is for the purpose of our algorithm crossing or not. Similarly with these and all the other examples. So you can see it's not that simple. So technically, the students who said they will want to be paid by hour were the smarter ones, because they knew it would take a lot of set of rules to create that algorithm. So what everything we can calculate with vectors. You can go again. You can just show me your ideas. So which geometric operations should a vector GIS be able to perform? Any ideas? What would you like your GIS software to be able to calculate for you? You might have come across some of them in your Esri tutorials. Anybody has any ideas what you can calculate? Should I vote? I don't know. There's nothing happening. Distance. Yes, thank you. Nice one. I'm on a plane mode. Okay, I'll keep that. The intersect point, the distance, area, angles, direction. Gradient. Optimal path, nice. Boundary, perimeter. Okay, let's leave it there, but very well. Submitted responses, thank you. Coordinates, yeah, I like that one. So you can keep sending responses, but I'll go back here. So let's see what we can calculate from some of these things you've mentioned. First one, distance. You all should be familiar with Euclidean distance, which is we do the typical trigonometry, distance between 2 points. That's the most used one. However, it's not the only one. We can have other algorithms, for example, for Manhattan distance, that would be used on rasters. And the number 4 I have will be in the raster neighborhood, in the 4 raster neighborhood. So imagine the grid of Manhattan. So if you go from point A to B, you won't go across the building, you would go around the grid. That's why the Manhattan distance is shaped like that. Another distance which we can calculate could be a chessboard distance. That would be also in rasters in 8 neighborhoods. So you can go like you would go on a chessboard. You can go in across the diagonal and then straight and up. So there's few different logics. However, in reality, we're actually not traveling directly from point A to B. We follow lines, we follow roads, we go across parks. So in reality, we actually measure distance following some networks. So I've noticed in some of your examples, that's a very good thinking, that we can measure some networks. So other distances we can have distance between boundaries. We can have distance between point and the line, something we call buffering, very commonly used in GIS techniques. This distance between areas. We can have a distance within a network, which I've just said, that I'm following a certain road segments to another and another, so I take the length of these lines. So that's also a distance calculation. Yeah, I don't know why. I understand why it can be confusing. Why would you call it a buffer? Because if you create a buffer, it creates a whole buffer zone, which is kind of more like a polygon. But let's say I'm interested only in one specific point. I can still detect the distance by looking at it from the buffer perspective. So I would have a line and a point, and this distance, it can go along the whole line, but it would be the buffer.
Does that sort of make sense maybe in a Google Map perspective, like when you said that a point is particularly in front of the coastal area, but there's, I guess, a sort of range where you say you reach your location. Kind of like when I search on Google Maps and I reach my location, I'm not at the point, but I'm maybe 2-3 meters around when it says you entered your
Yeah, that can be. But I mean, even if you go the other way around and you have a point and you're trying to find how far is a certain line, so you would create a buffer of, I don't know, 3 meters and search, is it intersecting already with the line? Is it touching the line? So how far is the line? So you would do that.
Would it just be a circle of radius 3?
Yeah, circular radius 3, yeah, you can do that.
Would that be a closed polygon?
No, it's called buffering. Generally, you do buffering around either points, well, you can do them around everything, but you're trying to find the zone within other features can interact with the feature you're creating the buffer from. So if I want to find which houses are near the road, and I want to cover the houses that are 3 meters away from the road, I would create a buffer along this road to find the points that represent the houses. That's why it says it's buffering. So you're finding the point, but you actually want to have it as a 90-degree angle. We try it like that. There. I don't know. Let's just, if this is my road, and I have houses here and here, so I will create a buffer zone around this road, but it's always taking the 90 degrees angle, so I know that this house is in this distance. This house wouldn't be because this would be further, so this is my buffer, and it's always using the 90 degrees of a distance. That's why it would be called buffering.
So the points you pick arbitrarily and are the points on the outer
No, the points that just have coordinates and are somewhere. So this is my road, and I'm interested in houses and how far they are. And if I know I'm interested only in those that are within 3 meter distance, I'll create a buffer around that will cover all of them. But it's doing the distance in 90 degrees manner from the road. That's why it would be called buffering. You wouldn't use it for usually just for 1 point, but for more, I guess. Yeah. Yeah. Oh, that was hard. My exercise. Very good question. Another thing we can calculate is the centroid of a polygon. So this is the formula. So how do we do it? We take all of the x coordinates of a polygon, all of the y coordinates of a polygon, make an average of each one of them, and then create, and then we'll get the coordinates. So let's calculate the centroid of this polygon. So how do we do it? So we can take the x and y, so 14 plus 67, 91, 106, 92, divided by how many? How many points there is? 5, yeah. I don't know it by heart, but you can do it. And the same I would do for y coordinate. So you can try it at home, but this is the result. So you'll get a centroid coordinate of this polygon. Makes sense? Okay, another one. What do you think? It's similar, but we have there. It's a different shape. Where do you think this centroid would be? Yes, you're right. It will be outside. So concave polygons, some of the concave polygons can have the point outside. As I already mentioned, concave because the angles within the polygon is larger than 180 degrees. So this one's larger than this one as well. You can also calculate the area of a polygon. I know you've mentioned areas in your field, so this is the formula, Simpson's rule. Easy to fill in, just you have to make sure that you go counterclockwise and then divide it by 2. You can go clockwise, you will get the same result, but it will have minus in front of it. And you want area to have positive plus numbers. So you look at the boundary points, you order them in a counterclockwise manner, and that's how you put them in your formula. Let's get a polygon. How would you calculate the area? Again, you fill in the x and y coordinates. I'm technically hoping you're doing it, but maybe you can do it later at home. I would recommend you do some of these calculations. It might be useful for later. So this is when we put it in. So we have the 2f is 8,000 something. And that's my area. point relative to line. We're going closer to how can we calculate if two lines cross. So we're looking at the relationship between point and the line. So generally we want to know if it's on the left or on the right side of the line segment. I think I have an example here. So we have a line and a point, but we don't know where it is if we look just at the coordinates. So this is again, that's the formula how it can be done. We have three coordinates. We have the point coordinate, the beginning of the line coordinate, and the end of the line coordinate. So we created a determinant from using these three coordinates, where the first place is always 1. So it's a scheme of 3 by 3 values, and then it's computed by using this formula at the bottom. Well, that's how you create the determinant originally. So you put the first column is always 1, then you have x of the point, which is the line of the first point of the line, y of the point of the first point of the line, x of the first point of the line, y of the finishing point of the line, and x and y coordinates of the point. You put them in like that, create a determinant, and you can calculate it. So that's the example. So we have start and end point, start coordinates, end coordinates, and the point coordinates. So we put them in. So this is how it can be done. And we have the determinant is minus 60. So it's less than 0, so it means that it's right from the, as you can see here, that if it's less than 0, it's right from the line. If it's more than 0, it's left from the line. And it's exactly 0, then it would be on the line. Line intersection. So now we're getting to what the students could have been paid for. So we have two lines, line 1, L1 and LP, with point 1, point 2, point 3, point 4. And we can decide if they intersect. So we're again using determinants of both of them. Generally, when looking at line segments, they can be either both. We'll start with line 1, and then we will look at the relationship of the second line to the first line we choose. So if I have a line in one, let's say I have a line like this, another line like this, I'll start with this one, and then I'm looking in the relationship with this line. If it's again, it's on the right or on the left of this line, that this is my original line, line 1. Similarly, like with the points. How can I do it? The basic logic is if I can find where a point, a relationship of a point to the line consists of 2 points, point 1 and another. So I can look at the position of these points. If this point is right to my line 1, if this point is also on the right of my line 1, then I would say they don't intersect. Yeah? In a case where I would have, this is the line I'm originally interested in, as the line 1 and line 2, we can see that this point is on the right side of the line and this point is on the left side of the line. So if they're on different sides, it means they probably intersect. The probably, I say, because there can be the case. They can be like this. So there can still be a space where they won't intersect. So they could intersect somewhere further if I would extend this line segment, but not in this case. So that's the logic of how we can use the position of point and line to determine if two lines cross. Does this make sense? I see some nodding, that's good. So if we go back to the determinants, this is really hard. So the first determinant of the line 1, and so this is from first point from the line 1, and a point from the line 2, first point from the line 2. Can you see that, how it's defined, point 1, point 2, so line 1, but the point is from line 2. And another line 1, but the point is from line 2. Yeah? Same goes for the second one. So this first point is from line 2, but this is on the first point. So you do it for both. You will look at this relationship for this one, and then you will also check if the relationship of this one, if they're all as well on the outside. Yes? Pardon? That means, I have it written here. At the same time, it means that they both have to be, means and. Yes, and. They both have to be true. If one of them is not true, then they do not intersect. And if we are interested in a point of intersection, we will create this determinant and make it equal to 0, which will then give us the coordinates. So let's look at a practical example. It might become more clear. So do these two lines intersect? Well, we can see they do because we have them graphically. But if we would have just the coordinates, how would we do it? So we create the determinants. So determinant 1 for the first line and on the top. First point, again, first column always 1, first point, second point. First point is from the line, 10, 10, from this origin line, line 1, and then the second point is 40, 20, and 20, 30, which is 40, 20, 20, 30. Yeah? And I go to the second determinant, I'll take the end point, and again take 40, 20, 20, 30. And then I'll do it vice versa for the other line. Then I would be looking at the relationship of those 2 points from this line. Can you see that in there? So you calculate the determinant, and they're both less than 0, as you can see. 200,000, is it 220? 20,000, 180,000, less than 0, they're both minus. So we can say that yes, the line segments intersect. And where do they intersect? Again, I fill it in the determinant with the P. The P is the point I'm trying to find, that's why there's X and Y, and I'll get the coordinates. Okay. Another calculation.
Why both of them are negative?
Pardon?
Are intersecting. Before, if we have like a negative number, that means that the point is on the right of the line. Yeah. And now we have, the determinants. Both equations give minus.
Yeah.
What is the criterion to say that now they are intersecting with two negatives? In the other case, if you study the position of the line or the point in reference to the location of the point in reference to the line, and you get negative value, that means it's on the right. So if you have 2 points and you study 2 points,
no, you need to have the.
Are on the right, that means that they are not going to intersect.
No, it will be, if you think about it from the point. Ooh, where's the point? you think about it from the point, wait, I'll show it up. We have the, if it's smaller than 0, then it's always on the right.
Yeah.
So you want them actually both be on the right to each other. If they would be both on the left to each other, it could mean that the points are not. Oh, this is. So depends on the perspective again, but this is my main line, and I'm trying to find. Okay, I'll create a new one. So this would be the 2 points of the other line. So I'm trying to find that they always have to be something on the right. So there is a point on the right or left, and for this one again, this one would be on the right. This point is on the right, and then this point, if I'm looking at it this way, would be on the right. So you need to have the truth that there is a point that is on the right side for each of the case of the line, for both of them. That's why you're looking.
Every point
if yeah.
refers to the other point.
If they both would be on the same side, you would get them both. Okay, well, let's say the mathematics behind it, if they're both on the same side, like here and here, you would get minus. If they're both on the right, you would get minus and minus, but then you're multiplying the determinant, so you'll get together plus. If they would be both on this side, plus plus times is plus, but if you have minus and plus, it will stay minus. That's why it has to be minus. Make sense? Ooh. I'm not going to push it all the way down because it's hard. I need to quickly, last thing we have, it's point in a polygon. So how do we determine if point is in a polygon or it's not? I'll show you 3 ways. Just show, you don't need to learn how this is done. There won't be any algorithms, but try to understand the logic behind it. So we have given a point and a polygon. Given a point and a polygon, and we are trying to determine the relationship between this point and a polygon, if it's either inside or outside. So the first option is using triangulation. So we divide the inside of the polygon into triangles, and then from that, knowing the relationship between point and the line, we can simply calculate where this point is. Is it on the right side of this line or inside? So we can determine which side of each line of this triangle that is. And if for each triangle we will get an answer that it's on the right side or left side, we can then say if the point is either inside or outside of the triangle. And because all of these triangles are within a polygon, if the point is within one of these triangles, we can then say that the point is in a triangle. Make sense? Another algorithm how to determine can be a sweep algorithm. And imagine that we have an array that cuts through the polygon, and we are trying to see if it's how many times it cuts through the polygon before it reaches the point. So thinking back about the Jordan's curve theorem, where he said that simple curve determines if a thing is either inside or outside. So if we get an odd number of cuts, if this line would cut the polygon only once, we will get an odd number before it reaches the point. We can then safely say it's one border only, so it's inside. If it would cut multiple times, if the point was here, so we have 1 and second, we get an even number, we know that it would be outside. The trick is we're not interested in the location. We're not trying to find the coordinates of this point. We just want to quickly know if this point is inside or outside of this specific polygon. Yeah, imagine when you're selecting a polygon on a screen, you have, countries, layer of countries, you will click you want to click on that specific polygon and it will be highlighted as selected. So the computer has to quickly do some calculation of where you've clicked and then decide which polygon it will show, which polygon is highlighted. So this is just one way we can do the triangulation, or we can do the parity check, this sweep algorithm. Another algorithm I will show you is sum of angles. So we know that the point is here. We will use some how to call it, some reference direction line. We can say that it's north, and then we count the angles from this reference line to each point, to the angle from each point inside this polygon. What's the sum of these angles? 360. Yeah, that's quite visible. So if it's 360, then we can say that the point is inside a polygon. How about in this case? What do you think would be the sum? Less than 300 or more? 360 or more? Okay, it actually says will be exactly 0 because we will have the same amount of positive angle values as negative. But you can try that at home. Okay, I have a couple questions, but I'll actually do my last one, not this one, which I would like to ask you before we finish. If there's anything you didn't understand in the last 3 lectures, you would like me to focus or bring up again. So you can put your votes for something you didn't understand or something you would like me to clarify. Or you can write it on a piece of paper and give it to me, and I can have a look for it for next lecture. Interpolation, polygon, wow. Just talking about points and polygons today. And we're running towards the end of the time. So feel free to put in answers. It will still show up even after the lecture. 3, 4, 6. Not sure. 5, 4, 6. Not sure what that means. But next week we'll be talking about networks and how can we represent networks. So you can look at some literature, recommended literature, to be more prepared. Or generally, if you search for networks, you'll have some ideas. And that's it for today. Thank you.